In the spring of 1901, a group of Greek sponge divers took shelter from a storm near a small island called Antikythera. Diving deeper than usual to wait out the weather, one of them found the wreck of an ancient Roman-era cargo ship, sitting on the seafloor for what turned out to be over 2,000 years. Among the bronze statues and pottery they hauled up was a small, unremarkable lump of corroded rock and metal, barely bigger than a book. Nobody on that boat had any idea they had just recovered one of the strangest objects in the history of human engineering. For decades, that lump sat mostly ignored in a museum drawer in Athens, cracked into pieces, coated in marine growth. It wasn't until 1951 that a British physicist and historian of science named Derek de Solla Price began seriously investigating it. What he found inside the corrosion made no sense for the era it came from. Gear wheels. Dozens of them. Precisely cut bronze teeth, meshed together in a configuration far too intricate for anything else known from the ancient world. The device dated to somewhere around 150 to 100 BC, a period when the most advanced machines historians expected from Greek civilization were simple water clocks and basic pulley systems. And yet here was something with over 30 separate interlocking gears, arranged with a level of mechanical sophistication that Europe wouldn't see again until the astronomical clocks built in cathedrals more than 1,400 years later. Price spent years trying to understand it using X-ray images, but the technology of his era could only reveal so much through the dense, corroded bronze. He published a theory in 1974 proposing it was some kind of astronomical calculator, but huge sections of the mechanism remained a mystery, its exact purpose still debated for another 3 decades. The real breakthrough came in the early 2000s, when a research team, including physicist Tony Freeth and astronomer Mike Edmunds, working with a group of international specialists under what became known as the Antikythera Mechanism Research Project, brought in a custom-built industrial X-ray machine capable of producing 3-dimensional tomographic scans of the fragments, a technology that hadn't existed in Price's lifetime. For the first time, researchers could see directly through the corrosion into the machine's original internal structure, gear by gear, tooth by tooth. What emerged was staggering. The device wasn't just tracking the sun and the moon, it modeled the moon's irregular orbital speed using a clever gear arrangement called a pin and slot mechanism, correcting for the fact that the moon doesn't move across the sky at a constant rate, a detail rooted in a genuinely correct understanding of orbital mechanics centuries before anyone had a mathematical model to fully explain why. It tracked the 4-year cycle of the ancient Olympic and other Pan-Hellenic games. It predicted lunar and solar eclipses using a cycle borrowed from Babylonian astronomy called the Saros cycle. And it even modeled the differing orbital speeds of Mercury and Venus using gear ratios matched closely to Greek astronomical theories described in surviving texts by figures like Hipparchus.
To operate it, a person would turn a small hand crank on the side. Inside, a train of interlocking bronze gears, some smaller than a coin, would rotate a set of dials on the front and back faces, showing the position of the sun and moon against the zodiac, a rotating ball representing the moon's phase, and a spiral dial tracking the calendar across a 19-year cycle, used to reconcile lunar months with the solar year, a genuinely difficult mathematical problem that Greek astronomers had solved with startling elegance. Nothing else like it survives from the ancient world. Nothing close to it appears again in the archaeological record for well over 1,000 years. That gap is what makes the Antikythera mechanism so unsettling to historians of technology. It isn't that ancient Greek engineering was primitive and this one device was an unexplainable leap forward. It's that this level of precision gearing clearly required an entire tradition of craftsmen, mathematicians, and instrument makers, refining the idea over generations, a tradition of which this single surviving object is the only physical evidence we have ever found. Ancient writers, including the Roman philosopher Cicero, mentioned devices built by the mathematician Archimedes and others that modeled the movements of the sun, moon, and planets. Machines that were apparently well known enough to be mentioned casually in surviving letters and philosophical texts. For centuries, historians treated those descriptions as likely exaggeration, or at best, simple demonstration models. The Antikythera mechanism suggests those ancient writers may have been describing something startlingly literal. Somewhere in the workshops of the ancient Mediterranean, there was very likely an entire lineage of instrument makers whose techniques, whose training, whose accumulated skill in cutting bronze gears to fractions of a millimeter simply vanished from the historical record, taking their knowledge down with whatever ships, libraries, and workshops were lost to time, war, and the slow erosion of empires. We happen to recover exactly one artifact from that entire lost tradition, dragged up by accident by divers sheltering from a storm, sitting in a museum drawer for half a century before anyone realized what they were looking at. It raises an uncomfortable question that historians still can't fully answer. If one fisherman's detour into a random shipwreck handed us this much, how much more of the ancient world's real technological sophistication is still sitting, unrecovered and unrecognized, at the bottom of the sea?